Hello everyone and welcome to this lecture in the Build DeepSeek from Scratch series. Today we are going to start an important topic, and that is with respect to quantization. So until now, with respect to building the entire DeepSeek architecture, we have covered multi-head latent attention, we have covered mixture of experts, and in the previous set of lectures we also covered uh, the third major architectural pillar of DeepSeek, and that's multi-token prediction. So after covering these three major pillars, we now move towards quantization, and that's the final pillar with respect to the DeepSeek architecture. So when I say quantization, if you take a look at the DeepSeek version 3 technical report, and if you scroll down below, you will see that we have covered until now the latent attention, mixture of experts, and multi-token prediction. So the architecture part of this paper is finished. Now, if you come to the infrastructures portion, they have this FP8 training, and these major aspects of the FP8 training are what we are going to cover in this sequence of lectures. So if you scroll down below, you will see that they have a section which is called as FP8 or floating point 8 training, section number 3.3, and that comes up on page number 14. This section is about the quantization which DeepSeek has implemented, and like several other sections of this paper, if you directly start reading this, it will be a bit difficult to really understand what's going on. So what I'm going to do is that in this series of 2 to 3 lectures, I'm going to explain the five innovations which DeepSeek implemented in their quantization routine. First is called as mixed precision framework. Second is called as fine-grained quantization. Third is increasing accumulation precision. Fourth is mantissa over exponents, and fifth is online quantization. Okay, so when DeepSeek released their paper, they had figures on each of these sections. So, for example, if you look at figure number 6, that is the figure which illustrates the mixed precision framework, which we are going to see in detail. This is the mixed precision framework. Then, if you look at these figures, which is figure number 7, they have part A and part B. So, part A is with respect to fine grained quantization, and part B is with respect to increasing accumulation precision. If you directly look at these figures, it may seem that there are so many building blocks over here, and what do these different colors actually represent? I plan to break it down for you so that you will understand it. The third or the fourth part is mantissa over exponents, and the fifth is online quantization. So if you see, they have a part called mantissa over exponents, and they have a part called or a section which is called as online quantization. So the way I'm going to break down these lectures is that before understanding any of these, we'll first need to have a brief understanding of what exactly is meant by quantization. So in this lecture, I'm going to very simply explain to you what quantization means, and starting from next lectures, I'll take you through all of these frameworks. So the next lecture may be based on these three: mixed precision framework, fine grained quantization, increasing accumulation, and then I'll have another lecture on mantissa or exponents, online quantization, and then we'll wrap up the quantization part. So let's get started with today's lecture. Uh, First, let me show you the main reference which I'm going to use today. So quantization, I'm going to use a blog um, which is written by Martin Rotendos. This is probably the best reference which I've come across to understand quantization. And I'll be referring to this blog in today's lecture where I explain to you quantization and what it exactly means. So let's get started with that. Okay, so DeepSeek is a large language model, right? So why does quantization come up in large language models, and what exactly is quantization? So if you look at the basic building blocks of a large language models, we have inputs, we have weights. Inputs are multiplied by weights and pass through activations, right? So these activations which we are referring to, they are calculated after, let's say, you get the product of the inputs and the weights, and these activations then serve as an input to the future blocks, etc. Essentially, what I'm trying to say is that there are a number of parameters in a large language model which multiply among each other, and then we have several summations which need to be done. So, for example, if you consider this entire large language model, if you look at the multi-head attention block, the multi-head attention block has several matrix multiplications, right? Like queries will be multiplied with keys transpose. So, if you focus on each of these matrices, if you focus on the queries matrix, if you focus on the keys matrix, elements of these matrices will be multiplied with each other. Similarly, if you have feed forward neural network, there are multiple parameters which will be multiplied with each other. The reason I'm telling you all of this is because parameters, when you look at every individual parameter, it occupies a certain memory. So there are parameters in token embeddings, positional embeddings, multi-head attention, feed forward neural network. And if you consider the scale and shift, there are parameters in layer normalization also. We have the parameters in the output layer. All of these parameters take up memory. So just like if you are building a house, the house will take up some area, right? Similarly, whenever you define a parameter, that parameter takes up memory. The amount of memory a parameter takes up is determined by how we represent that parameter, right? So there are several representation techniques. The most common by default parameters are represented as floating point 32 values or FP32. For example, if a parameter is 3.14159, let's say, the way it's represented in memory is by these 32 bits. So if you count these bits, one bit, then we have 1, 2, 3, 4, 5, 6, 7, 8. There are 8 bits over here. So and then finally we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23. So 23. So if you add 1 plus 8 plus 23, that gives you 32 bits. So in this case which I'm showing you, the every parameter is represented by 32 bits in memory. What each of these bits mean is slightly different. The first bit controls the sign. So as is mentioned over here in this block, if you see, yeah, the first bit over here controls the sign. The second bit or this set of bits is called as the exponent, and this last set of bits is called as the significand or the mantissa. So essentially, there is a simple formula through which how the sign, the exponent, and the mantissa all add up together to represent the entire number. The number of bits which you have in the mantissa in the last part controls the amount of precision with which you can represent every number by. Okay. So at the top here, I am showing you a floating point, a floating 32-bit representation. And if you take a closer look at this blog over here, let's see. So if you take a look at the floating point 32 representation, and if you scroll up below, you'll see how these sine, exponent, and mantissa work. So sine is actually pretty simple. Whatever the value here is, you take minus 1 raised to that. So if it's 0, it means it's positive because minus 1 raised to 0 will be 1. If it is equal to 1, that's minus 1 raised to 1. So it will be a negative number. So the first bit determines the sign, right? The second bit, which is the exponent. So it's in this case, it will be 2 raised to 1. And the last part, which is the mantissa, which will be 2 raised to 0 plus 0.5701570312. So that will give us 3.140625. That's float 16 bit. For float 32 bit, it will be much higher precision. So if the same parameter right now is represented as a float 16 bit instead of a float 32 bit, it will just take 16 bits in memory. So it will take less amount of memory, but the downside of that is that we'll have a lesser number of bits in the mantissa part, right? So that means we will have a lower precision. So that same number will be represented with a very high precision over here, and that same number will now be represented with a very low precision in a float 16 bit, right? So essentially, what I'm trying to say is that every parameter takes up memory, and the amount of memory a parameter takes up is determined by how it is represented. If it is represented by 32 bits, it takes more memory, and the parameter can be represented in a higher precision. If it's represented by 16 bit, it takes up less memory, and that parameter is represented in a lower precision. Now here I have shown that if we are representing a parameter as 64 bits, and we have a large language model with 70 billion parameters. The amount of memory the all the parameters take is 70 billion multiplied by 64 divided by 8. The reason we are dividing by 8 is because 8 bits equal to 1 byte. So if we represent every parameter of a 70 billion model as a 64-bit floating point number, it takes 560 gigabytes of space. If we represent every parameter as a 32-bit floating point number, it takes 280 gigabytes of space. And if you represent every parameter as a 16-bit number, then it only takes 140 gigabytes of space. So the if you reduce the number of bits a parameter is represented by, the amount of memory that parameter can take will significantly reduce. And that's exactly what is meant by quantization. So if you look at the definition of quantization, quantization aims to reduce the precision of a model's parameter from higher bit widths to lower bit widths. So essentially, if a parameter is represented as 32 bit, quantizing means we represent that same parameter in lower bits right now. So if a parameter is 64 bits, we'll represent it with 32 bits, or we can represent it with 16 bits. That's what's meant by quantization. So you might be thinking, why would we do this? So I understand that we save up memory, but what about the precision which is lost? So it turns out that there are in several operations which are involved in the LLM architecture. It's fine if we lose out on some precision as long as overall the precision or the accuracy is maintained. So it turns out that we don't need to represent everything as floating point 32. Even if we represent parameters with floating point 16, for example, it might still lead to good results. So then why would we not do that? That's why people convert floating point 32 into lower bit representations while still we maintain the accuracy of the large language model. That is what is meant by quantization. So one image which I love in this blog is that if you take a look at the original image, whereas if you take a look at this quantized image, if you look at it from far, both of them look kind of similar, right? But if you zoom in, you will see that the original image is much clearer, whereas the quantized image is quite pixelated. So that's shown in this inset, right? If you zoom in here, you'll see that this inset is much more sharper than the quantized. The reason is because in the quantized image, it's only made up of 8 colors, 8 distinct colors, whereas the original image is made up of much larger set of colors. So this illustration just shows that if you do quantization, you take up less amount of memory, you take up less amount of space, because now this quantized image has lesser number of colors or pixels which have been used to represent the image, but we kind of represent the original image itself. It's not like we are getting a huge amount of reduction in the performance. That's why we do quantization, because we also get memory reduction while performance is not hampered that much. It's important to keep in mind that performance slightly degrades because the parameters lose their precision, but overall it does not hamper the performance that much. So now I just want to mention or quickly explain some quantization techniques which are very commonly used in which will also come up in the next lecture on how DeepSeek implemented quantization. So if we want to go from floating point 32 to floating point 16, this is how it is done, right? So floating point 32, we can represent a much larger range of values over here. Whereas if we go to floating point 16, we can represent a much smaller range of values. So for example, in floating point 32, the minimum value is minus 3.4 into 10 raised to 38. The maximum is 3.4 into 10 raised to 38. Whereas in floating point 16, the minimum value is minus 65504, the maximum is 65504. And you will also see that the precision is reduced. So 3.14159, here there are so many decimal points, right? But if you consider floating point 16, the precision is reduced and the range is also reduced. But this schematic shows how you can quantize a number from floating point 32 to floating point 16. In the next lecture, you will also encounter something called BF16. That's essentially brain float 16. So BF16 has the same number of bits as floating point 16, but it maintains the range. So you see, in floating point 32 to floating point 16, we reduce the range, right? But from floating point 32 to BF16, the range is maintained. The BF16 also, the minimum is minus 3.4 into 10 raised to 38, maximum is also 3.4 into 10 raised to 38. but the number of bits are still equal to 16 in BF16. So that stays the same between BF16 and let's say FP16. And the third is integer 8. So that's the lowest form of representation, where the minimum and maximum go from minus 127 to 127, and only 8 bits are represented over here. That's why it's called as integer 8. So here every value is essentially an integer. We don't have decimal places. So if you see the three types, or the four types rather, we have FP32, we have FP16, we have BF16, and we have int 8. So already if you take a look at the DeepSeek, the first schematic which they have in the quantization section, you'll see things like BF16, you'll see things like floating point 8. Now you should be able to understand what FP32. FP32 means floating point 32 representation. FP8 means floating point 8. Here I showed you integer 8, right? FP8 is similar to FP16, but we go one further level below. So what I showed you here is FP16, right? FP8 is one more level below, where we go from minus 127 to 127 and allow floating points. Then FP, we have FP8, BF16. I showed you BF16 already. That's brain float 16. Then there is also FP32, which also I showed you. So now when you see these schematics, you should be able to understand what FP8 means, what BF16 means, what FP32 means, etc. Those are the quantization levels. Now the way quantization is actually done is that if you have a number which is represented in floating point 32. Let's say these are the set of numbers which are represented in floating point 32, and I want to represent these numbers in integer 8. So they will be from minus 127 to 127, right? The way it's represented is that um, in my given set, I first take the maximum value. I divide all of these numbers with the maximum value. So if you have a number x, I divide it with alpha, and then what I'll do is that I'll multiply it with 127, because that's the maximum value which can be taken in integer 8. So what that does is, so if you have this minus 7.59, this will be minus 7.59 divided by 10.8 into 127, and then I take the closest integer to this. So that will give me the representation of minus 7.59. Similarly, all of the numbers which are in floating point 32 are now brought back into uh, integer 8. So this calculation which I showed you, here we have to divide with the maximum number, right? This will play a very important role when we are going to look at an innovation in DeepSeek, which is called as uh, fine grained quantization. So to understand fine grained quantization, you will need to understand what I am explaining right now. If you have floating point 32 numbers, and if you want to convert them to any quantized, let's say integer 8, you first divide all of these numbers with the largest value. So you divide all of the numbers with the largest value, and then you multiply with 127, because that's the highest value, let's say, which integer 8 can take, right? That's the way you quantize from floating point 32 to integer 8. So this division of the highest value is very important here. So that's where you get that broad level scale, and then you bring it down. So we have the broad level floating point 32, and then we bring it down to integer 8. These many concepts, I believe, are enough for you to understand the next lectures in quantization which are to follow. So once you have this basic understanding of why we need quantization, because it reduces the memory usage while still maintaining the precision, and you should also know the different representations, such as what is meant by floating point 32, which means we have 32 bits. Floating point 16 has 16 bits, and the range is also reduced in floating point 16. BF16 maintains the range, well, whereas we still have 16 bits. Integer 8 has only 8 bits, and the range is much more reduced, minus 127 to 127. And to actually quantize, what we do is that if we have floating point 32, we divide every number with the maximum value, let's say, and then we multiply it with 127. So that takes me from uh, this initial floating point 32 and brings me back to minus 127 to 127. These many concepts will be relevant for you to understand mixed precision framework and fine grained quantization, which we'll see in the next lecture. And after that, we'll also see increasing accumulation precision, mantissa over exponents, and online quantization. All right, so we are now slowly making inroads into more deeper and deeper aspects of DeepSeek. So, for example, if you take a look at their table of contents, we have finished the whole architectural implementation, and now we are slowly going into infrastructure. In this series, we are not going to look at too many hardware related aspects. So, I'm going to look at quantization only, and then we'll go to the next chapters. Thanks, everyone, and I look forward to seeing you in the next lecture.